Glad to be here. Just a really quick blurb about me. I'm a software developer. I've been doing this since I was about 7 as a hobby, so that's several decades ago. I won't say how many. And I've been doing this professionally for about 20 years. I love writing code. I love solving problems. I've taken the sort of the same path that everybody takes. I started out with like basic hacking. Can I write something in BASIC that makes this computer do something? And then I started learning formal languages and computer science and all this stuff. And I've found over the years that I've adopted a lot of paradigms. And the one that is most exciting to me now is functional programming. I'm going to talk a little bit about what functional programming is, what it looks like, why you would want to consider using it, and how to go about making the kinds of changes that get you the low-hanging fruit, the biggest benefits for the least effort when you take object-oriented code and start shifting it into a functional paradigm. So my goal is that I show that functional programming offers both immediate and also long-term benefits and should be part of your toolbox. Whether or not you use it completely for everything or just as an extra tool, that'll be a balance you'll have to figure out for you. So what is functional programming? Well, functional programming is essentially the removal of all state from your application. That is to say, right now you have state in the form of variables and you have state in the form of objects that have properties, and you have all this state. And functional programming is about finding state and removing it. To which most people will say, what? Like, if I remove all state, what do I have left in my program? And we will address that. But I want to point out the difference. State within your program is very different from state outside your program. And within your program, if you can remove state, if you can remove the kinds of changes to data that lead to the most common programming bugs, you can gain benefit. So functional programming looks at your code and says, what if all data were immutable? That's really the question it's asking. What if all data were immutable? What if every variable I pass, the function I pass it to is not going to change it? I have a variable. It will always have the value that I set it up with. I own it, and nobody else can change it. And if you have that base premise, you have the foundation for a very powerful programming paradigm. Functional programming's background comes from things like telephone switching systems in the 70s and 80s, deep space exploration vehicles where a single bug can cost hundreds of millions of dollars, and a lot of other places. But ultimately, like I say, it's just reframing your architecture style to ask, what if data were immutable? What can I gain from that? As a reminder, all a function is, and really all a program is a transformer of data. You have some input data, you have some output data, and it's the transformation in between that you're interested in. And so functional programming addresses that directly. Let's talk about transformations rather than state. Additionally, with functional programming, it's a lot of things to a lot of people. If you ask any 10 people what functional programming is, you will get 10 very different answers. Some people will talk about buzzwords. You'll hear about things like tail recursion and declarative this and that, and a whole bunch. You'll hear a lot of things being thrown around, but really it is that removal of state. And in a slightly more defined terminology, you're changing imperative code, we'll talk about that in a second, to declarative code. And so if you've heard those terms, imperative is also called procedural. So if you're used to hearing about code being procedural, what functional programming is looking at procedural code and making it declarative instead. In imperative code, you have statements that change program state. So functions like x equals y times 3, that's imperative. You're taking an expression and assigning the value of that to a variable. In declarative code, you use expressions only without assignment. And that's not 100% true. There are cases where assignment happens, but what you're looking for is you're using expressions that state that describe what output you want to get, rather than writing code that walks through your input and generates the output. So it's just a slightly different framing on things, and we'll see examples of exactly what this looks like in practice. But ultimately, we want our code to be comprehensible and testable and maintainable, and declarative code happens to be much more comprehensible and much more testable and much more maintainable than imperative code, because the number of things you have to check to know that your code is right is greatly reduced. Also, it might not surprise you to find out that functions are at the heart of functional programming, hence the name. we're really going to take a focus on functions and what they are and what they do. So let's ask the question then, what are functions? And functions are, I mean, everybody knows what functions are, but nobody really knows what functions are, right? There's actually a lot of mystery to them. Functions are essentially some kind of object. In Python, they're objects. In most languages, there's some kind of token or word that you've defined that can be called. You pass them parameters and they give you a value back, right? At the very core, that's what a function is. You call a function, it gives you a value. The value it gives you might be a list of things. It might be an object that's very complicated, but at the end of the day, it gives you back one thing, or a tuple, which is one thing that contains within it many things or whatever. But it's something that can be called that returns a value. If you think about it, though, there's a really cool extra corollary there, which is that because they're just objects, functions can be passed as parameters and returned as values. So if we look at the examples on the right here, is my cursor visible? Can you see my mouse?
Yes.
Okay, so if we look at this example, we have this function called evens, given a list of numbers, some kind of thing we pass in. We'll just pretend it's right here. You can see an example at the top. Given a list of numbers, we want to get all the evens out of that list. So the kind of the naive way or the novice way that you learn in basic programming is you build an empty array, and then you iterate over your iterable. You go through your list, and for everything that matches some requirement, you add it to the new list you're building. And then you return that new list. And we've all written this code before, right? This is intro to Python. Somewhere in there, you're going to write something like this. And if you call that, you can see that you get the result like 2, 4, 6, 8. You get the evens out of the list. But there are other ways to get that same effect. And I want to show some examples of those other ways to talk about the implications of them. The first is using comprehensions. And Trey Hunter has a great talk. I've heard him give it at PyCon and at DjangoCon, but he's given it at several additional locations. He has a great talk about comprehensions and generators and what they are. Essentially, a comprehension is a way of declaring, back to that idea of declarative code, declaring that I want my output to be a thing, a list, that has these elements in it. And so in this evens list comprehension, what we're saying is we want to receive a list that has every number in our original list if that number modulo 2 is 0. So if the number is even, include it, and if it's not, skip it. While this does exactly the same thing as the first method, it happens to be more performant, but also it happens to be a lot easier for the average person to look at and understand. Once you get used to comprehension syntax, I can glance at this and tell you almost instantly what it does, but the upper one, there's more that I have to follow. There's variable assignments, there's questions about what is the value of this variable, that all things are going on in sort of a way that is slightly more difficult to piece together in my mind. Once I learn the syntax, reading this comprehension syntax, which does exactly the same thing, becomes more natural. Now, besides a comprehension, this next example is a variation on comprehensions, which is a generator. The only difference between a comprehension and a generator, I say a lot of things that are sort of stepping on landmines. At a high level view, the only difference between a comprehension and a generator is while a comprehension is returning a type of shall we say, fully resolved object, it's returning a list or a dictionary. A generator is returning an iterable that you can sequence through and get all of the values. But for a variety of reasons, it happens to be use less RAM, use fewer resources at the time of generation, and defer those resource uses to the time of generation. The time of when you actually query for the next value and the next value. So it defers some of your work. But the main thing to note is that the output of the generator is basically, for all intents and purposes, the same as the output from the comprehension. One returns a list, one returns an iterable, and if you iterate over each of them once, you'll get the same values out. So this is a generator. You could also write this in a more like statement-oriented way and end up with what's called a generator function, but I'm not gonna really talk about those. Another way, if you wanted to find all the evens, would be to use a filter. And filter is a built-in function in Python. It's part of the core language. And you'll notice here that filter takes some kind of test, followed by the thing that you're iterating over. So we're iterating over our numbers, and on each number, we're performing this test. Now, the thing to note here is this test happens to be a function. This is us passing a function as a parameter. So functions aren't just things you can call, they're also parameters, or they can be parameters. How exactly filter works is not the point, other than just know that you can pass functions as parameters. You can either pass a function using a lambda, which is a shorthand way of saying this function does this thing, or you can pass a function as just name the function that goes here, and that function will be called on every element, and the result of that function determines if it's included in the output. And then, and again, if you don't understand the syntax of these specifically, this is more just to give you an idea that there's more than one way to do it, and that some of these ways have some interesting features about them. This last one is a function that returns functions. And what I mean is you call this one time and you pass in the list of numbers that you want to use. And what it does is it gives you a function that you can call as many times as you want. And each time you call it, you get back another iterable that you can iterate over from that list. So if normally with a generator, you iterate over it once and then you have to go reset the generator and restart over. So this is a way of saying, well, when I call my function called evens repeatable, what I really want you to do is I want you to actually call this other function and send it these parameters in this way. What I get back is a function, so I call the thing I get back. So if I call evens repeatable, it gives me back a function that I can call. So I'm calling that function evens again. And every time I call evens again with open and close parenthesis, what I get back is that list of evens. So functions can be passed as parameters, functions can be returned as values. And mostly I want to make sure people are familiar with that conceptually, because once that's true, there's a lot of theoretical mathematics that we can use that's beneficial to us. And in particular, functional programming really is just a fancy way of saying that we're using Lambda Calculus. I highly recommend you learn about Lambda Calculus. You've probably had some exposure to it already if you have a CS degree. Lambda Calculus is basically the mathematics of functions. And it turns out that Lambda Calculus by itself is Turing complete, which means that anything you can write in software, you can write in purely functional paradigms. And that's important because when people say, well, we don't have state, I can say, well, in fact, that doesn't matter. We can still get our application to do all the things we need to do. I'm not going to really dive on that in depth. I just want to point out that if you go read about Lambda Calculus, it'll give you a lot of ideas about the background of functional programming. And what that gives us is things like formal provability. This thing really is correct. It also gives us composability and testability and debuggability and all kinds of other useful things just by following theoretical mathematics the same way that we follow basically algebra to know that we got our math right in our function. We're using Lambda Calculus to know we got the algorithm right with our functions. There's a couple great talks I want to point people to. A lot of my background in functional programming really stemmed from watching these talks, so I'll point them out specifically. One is called Functional Programming in 40 Minutes. Russ Olson gives a great talk about the mindset behind functional programming. Like you've heard about this thing, it sounds like a great idea, I want to try it out. He gives a really good talk about how to start reframing your thinking in terms of functional programs. And he addresses specifically no state, no side effects. I'm not allowed to have my code can't do anything. He quotes one of his coworkers as saying, initially it feels like wearing handcuffs, but after a while those handcuffs feel like a bicycle. At first, removing state from your code is painful, but once you get used to how to do it, it actually becomes quite liberating. Your code becomes easier to read, easier to understand, easier to modify. But he also points out, and this is really important, that we are not in the software business. None of us are. We're in the side effects business. Nobody cares that your code executed. What they care is that the database got updated or a notification got sent or some actual side effect happened. It's the side effects that we're being paid for. So we want to ultimately have side effects. Like that's what we actually care about, changes to the database, updates to some system somewhere. But within our application, if we can get rid of side effects inside the code, it becomes much easier to reason about how it works in the world as a whole. So I recommend that talk. Another talk I would recommend is called Why Isn't Functional Programming the Norm? This is basically a history lesson. Where did object-oriented programming come from? How did we get here? Why is object-oriented so popular? And in his mind, and I happen to agree with him, it mostly got there by accident. It's not that object-oriented is the end all. It's that it solved some problems in a way that people happen to adopt in mass, but in a way that also adds complications. And if we could go back and do it all over again, it is probably unlikely that object-oriented is the way that modern software would be built if we could go back and start over. But we are seeing the industry change. Functional programming is becoming more and more prevalent on a regular basis. So anyway, with that kind of as like some framework and background, I want to show some of the patterns that I use when I'm converting old or legacy code into functional code. And to do that, there's a whole bunch of patterns. Just like any design pattern course, you'll find that there are thousands of patterns and lots of different names for the same thing. But I've found that there's about four patterns that I use every single day in every bit of code that I write when I'm refactoring or improving my code. And there's a couple more that just happen to be object-oriented specific. So I'm going to talk about the four big ones. And keep in mind, this doesn't matter if you're object-oriented or not, you can start doing some of the things in all of these patterns to make your software provably better. So what are those patterns? Well, there's copy to modify, and we'll dive on each of these. Replacement statement with expression, replace loop with generator, right? Just patterns for you have code in state A and you want to get it to state B, how do you get there? So I'll kind of walk through what some of these look like. The first one is copy to modify. So remember I say we have no state and no side effects. Well, the side effect is where something that I do now impacts some other function call later in a way that can't be necessarily predicted or is hard to follow. So for example, if you give me a list and I change the third element of the list, then your copy of the list also has that change, and that might not be what you wanted. I know that I need the list with the third element different than the one you gave me, but other people you pass that list to might not be expecting that change to happen. So if I want to modify something, I'm not going to modify it in place. I'm going to create a copy of that item, a shallow copy, right? It's just a pointer to this object and this object, and like, it's just variable references, right? Object 1, object 2, object 3. And in the copy, I'm going to have pointers to the exact same objects, but the third one will be changed to point to some different object. Everything else in the list is it's not a deep copy, it's just a shallow copy, so they can see the list with one thing changed. So one way to do that would be with a list comprehension, or in my case, a generator. This top function, you call it, it changes an element in the list. It probably does some other things too, right? Replacing just that one item, you'd probably inline that, right? So this function does a few things, but as a side effect, the list is changed. In mine, when you say I want to replace an item, it gives you back an iterable. In this case, it's a generator, so I can only iterate it once, but I could do the same thing with a list comprehension or other structures. It gives me back a generator that when I iterate over it, gives me all the same elements as the first list, except the element that I indicate has been replaced with a new value. So I'm working with a copy of the list, not with the list itself, which means any other user of that list is unaffected by the things that my code does. That's how you eliminate side effects. You eliminate side effects by looking for places where your code changes something that somebody else might be referring to. So copy to modify. If I'm going to modify anything, I make a copy of it first and then do whatever I want. I can have a field day with the copy, but I leave the original item alone. The next pattern that I find myself using a lot is replacing statements with expressions. So a statement is anything that has an equal sign and something on the left and something on the right. Again, it's probably a little more complicated than that. I don't remember my computer languages terminology perfectly. There's probably a little bit more refined definition to a statement, but basically it's generate some value and assign it to some variable. With functional programming, I want to get rid of statements as much as possible. So how do I do that? Well, I look at where the assignments are happening and I do the same computation. In this case, this is to decompress a zip file that is in RAM. So I create this archive object by calling the zip file function in the zip file module, pass to it the bytes of my content. And then the next thing I do is I go look up the name of the first item in the list, and then I return the contents of the first item that was in the zip, whatever that first item is. Right, so I've got a couple assignments. I'm figuring out what archive is, and then I'm figuring out what first file is from archive, and then I'm calling archive read on this first file object. In the second version, what I've done instead is the first function sort of does the figuring out part. What is it that needs to be opened and retrieved. And the second function does the actual retrieval part. So the first function does this same call to zip file that was done in the first one, but instead of assigning it to a variable, it makes it the parameter to another function. Then it calls that function, and that function now has the archive parameter, and it can do all the things it wants with archive, but nothing that it does in here is dependent on archive being anything other than just a parameter. Like, it's not changing the archive, it's not trying to do anything, it's just accessing it by name. And if I look at this code, it's easy to think of how I would test this, where it's harder to think of how I would test the first one, because I have to think of corner cases and conditionals. By making it functional, I'm removing the number of things, I'm lowering the number of things I have to test and the complexity of testing those things. So you look for places where you have statements and see if you can extract a function call from them and use that function call and pass to it what would have been the value of some variable. So instead of assigning this to archive and then continuing iteratively, imperatively through that, like I say, call a function and pass to it the computation that determines what the parameter should be. In general, find ways to extract inner functions and call them with resolved intermediate values. That's really what that's saying. And in some short functions, you might actually leave it imperative. You might leave, like in this function, it's actually small enough and simple enough, I might leave it this way. But the pattern is, if you see something like this, look for ways to break it out into separate functions, because then those individual functions can be tested much more readily. Another pattern that's really handy is replace loop with generator, replace loop with comprehensions, replace loop with X. Anywhere that you're looping, if you find yourself doing a for loop or a while loop, there is a comprehension that will do the same thing. There is a generator that will do the same thing. So look for places where you have loops and instead break them out into constructs that are declarative, like this generator that you can see down here. In the first one, we're creating an empty list. We're iterating over the input, and for each thing, we're appending something new to the list. We're constructing a list in real time. And in the second one, we're just saying, given this input, each time I ask for another item, just give me the length of the next thing in the input, right? So I can reason about this second version a lot easier. I can test it a lot easier. Again, it's that idea that by removing the kinds of things that have state that I have to think about, I'm making the code easier to understand, easier to follow, easier to maintain. There's so many things that you can do with iterables, like lists and dictionaries and anything that can be iterated. The iter tools, the entire package is basically a bunch of meta patterns for iteration. So things like taking two lists and merging them into a single list, or grouping things by name or by age or whatever, finding combinatoric combinations of things. Right? There's a whole lot of things. If you think about how iterables work, they end up being sort of a wonderful base type to use for a lot of different algorithms. And so look for places where you have loops and replace it with some kind of iterable, like a generator, that you can express much more readily what you're trying to do. If you take those last three together, what they really are is a meta pattern, which is decompose function. You can see on top here, I have a function that has statements. It has a variety of different things going on in it. If I wanted to test this, I can think about, I have to test what if the file doesn't exist? What if the file name doesn't contain a dot? What if the file, like there's a whole bunch of places here where I have to think about what logic do I need? What input do I have to put in to make it follow the right path through my code to get the right answer? And what I really want is a bunch of individual functions that individually can be tested very readily, and then maybe one or two integration tests that test the whole thing from front to back. So in the bottom here, I've got a function that wraps the with statement and hands off all of the work to another function called execute pipeline. And it takes as an input a pipeline. So I have another function called build pipeline, and it builds it from a file name. So I can look at these. If I wanted to test build pipeline, I test, if I give it a file name, does it give me the right object out? And if I want to test execute pipeline, if I give it a list of functions or a list of callables, which is what my pipeline is, and file, does it give me back the processed file with all the work done? But at no point am I having to think of, how do I test this for this case and this case? It's more like, given this input, do I get the right output? Okay, good. That ends up being a pretty easy thing to test. without side effects. I don't have any like mocks that I have to set up. I don't have any weirdness I have to do. I can simply give it an input and make sure I get the right output. So decompose your functions down to their core components, down to their base parts. I'm going to flash through these next couple. It turns out they're super easy. Once you've decomposed your functions, once you've gotten rid of all your state, and you do things like make any variables you use inside the function, make that into a parameter rather than something that's passed as attached to self, something like that. Once your functions don't have any internal state, then it's very easy to just move that function to the top level and make your function the thing you call rather than having a class that you call functions on. And that means testing the things in your class doesn't require instantiating a class and thinking about how you would set it up. It just means you call the function and make sure you're given the right input, you get the right output. So there's value in simply getting your methods out of classes unless they have to be in classes. But if all your behaviors are defined as functions and you've gotten them out of your class, then all your class does anymore is simply hold state. And we want our application to be stateless, so we're not going to have state, so we don't need the class. We can just eliminate the class. So essentially, we're looking at ways to decompose functions into their core parts, describe them in a way that's declarative, so they're easy to test, easy to reason about, and simplify the architecture by focusing on the algorithms rather than on the infrastructure to express how state is managed. Ultimately, at the end of the day, what we're really looking at is rethinking how you think about code. Think about, what if I didn't have variables? What if data were immutable? What if I couldn't change the values of the things I had? How would that make writing and debugging and maintaining my code easier? It turns out it makes it easier in a lot of ways once you get used to it. So how do you make your data immutable? You decompose functions, you eliminate state and side effects, you change your imperative code to declarative code. And at the end of the day, what ends up happening is it really is functions all the way down. Your function calls somebody else's function, which calls somebody else's, which calls somebody else's, and ultimately it calls some system function at the low level, and it's just functions all the way down, and we're in happy land. And the major benefit that I've gotten from this over several years now of doing it is that my code is easier to understand, easier to test, easier to reason about, and a few simple libraries where I just keep, like in Evernote or whatever, where I just keep, here's a function that does this, and here's a function that does that, makes it really easy to quickly get a new program up to speed because I've got utilitarian functions that do the kinds of transformations I want. So then my question is, what are the transformations that happen in this application? Okay, now I have to write the functions to do those transformations. There's so much more I could talk about, and there's so little time to do it in. So what I'm going to do instead is open this up for questions and encourage you to watch the talk that I did the other day where we take these ideas and practice them. In a 2-hour process, we walk through from start to finish, taking an object-oriented program and converting it to purely functional code. So I would recommend you go look at that. But at this point, I would love to answer any questions people have. I kind of sped through a couple parts of that faster than I wanted to, and want to open the floor for clarifications or revisiting any ideas.
I have a question. How does this affect performance since you're instantiating new like an array? You're essentially...
That's a great question. So functional programming is making a trade-off, and the trade-off is you're trading off RAM and some clock cycles, but in practice it ends up, if you do it well, it ends up being not many clock cycles, but you are trading off RAM because you're doing a lot of object instantiation. For what you're getting in return for that is comprehensibility and testability. For certain algorithms, it ends up being problematic. For example, if you're reading an entire file into the computer and then trying to work with it, if the file gets big, you're going to crash, right? You want to look for ways to do that in a performant way. But the way to do that is not to change to a different paradigm. It's to think about, instead of loading the file all at once, what if I read the file in pieces? And you can do that with object-oriented, but you can also do that with functional. So the biggest performance hits that you're going to see are more about, in the short term, there just happen to be a lot of little objects getting created and destroyed. But Python happens to be pretty performant with that in general. So unless you have a performance test that shows you it's a problem, I would assume that in general, it's going to perform about the same. Plus, when you decompose your functions, often you will find a much more elegant solution to the problem at hand that eliminates the very thing that caused some of your other performance hits. So by forcing you to look at your code differently, you find new ways to optimize that you wouldn't necessarily have found. That is a side effect of the process, not a first order goal. But you will find it makes you think about your code more, and which in turn makes you think about performance and all these other things from a more educated perspective. But in general, you are trading off RAM for understandability. And it happens to be that RAM is cheap and clock cycles are cheap. So at this point in time, that's a reasonable trade-off in general.
A question, Jeffrey?
Sure.
Very early on, you had the slide about the evens, and it was doing mod 2.
Yeah.
Is there a way, I know with strings, you can tack on like dot sort, and then you can tack on something that'll look for unique values. Mm-hmm. Can you do that?
You can. I'm not going to jump into a screen share. I mean, into an editor or live code.
Yeah, yeah.
But essentially, sorry, I got myself. I derailed myself. Please ask the question again.
Yeah. So the middle there, where you have def evens list comprehension, let's say. Mm-hmm. The return, can you say return dot sort dot unique or something like that?
Oh, I see what you're saying. Okay, yeah. So I would contend that if you wanted to sort it, so if you have a list and you call dot sort on the list, it sorts it in place. So everyone who's looking at that list will see the newly sorted list. So in that case, you also want to generate a copy and then sort the copy. And probably I would do that by passing the list into the sorted function. Along with a lambda that, the sorted function takes a function as one of its parameters. You tell it how to tell if an item is greater than or less than its neighbor. So I would call the sorted method on the results of, say, the evens generator. So that's 2 function calls, one to sort it and one to generate it. But the end result is you'll get the list sorted, but it's still your own copy, rather than modifying somebody else's. And again, there's that RAM trade-off. You have copied the list at that point. To be able to sort it, you did have to do at least a shallow copy of the elements. But what you get in return is knowing that nobody else is affected by the things you're doing. So some other method that's unrelated won't suddenly have a bug crop up because you just introduced some new sort, or something. Because those bugs are a pain to track down, right? That's painful when you have a side effect bug where it happens on Thursdays at 3 p.m., but only if the person's in Japan, right? Those bugs are a pain in the ass, but those are what side effect bugs look like. Anything else?
So making these big chains and kind of creating that like solid flow of data instead of like stopping as declared variables. Mm-hmm. To me, I'm having a little trouble with, as far as it being easier to debug. Mm-hmm. The way that I debug normally is I would look at what those variables are as the pieces are resolving. Mm-hmm. But with it just flowing and building, how would you be able to see what's causing a problem and what's not in that chain, because the chain is just not finishing?
Sure. So one way is to give it small sample inputs that are very finite in size. Like give it, for example, an array that has, like, okay, so for this one, which returns the lengths, given an array of strings, it gives you the length of each thing in the array, or an array of any kind of countable, objects. It gives you the length of each one. If I think about writing that as an imperative way, like I have in the top here, in this case, it's fairly trivial, but I still have to think about what are the boundary conditions. What happens if I give it an empty list? What happens if I give it a list that's huge? I have to think about the kinds of things that could go where it could go wrong. But to test it, what I want to do is I want to give it some input and get some output back and make sure the output matches the input. So the first few tests are going to be, I give it this array with 3 or 4 items, and I tell it to, I know what the lengths of them are. Actually, I think you were probably more asking about, was it this one? Well, yeah, this one's relevant too to that. So in this one, all I'm doing is I'm avoiding assignment. It's not that I'm not doing the same computation. It's just that I'm avoiding assignment because assignment can later bite me in the butt. So in terms of testing, these functions, I'll give them known inputs with expected outputs and make sure that the output I get just always matches the input. If it's returning a generator, then in my test, I'll convert that to a list, and then I can just go element by element and see, did I get the right things? And as long as I'm dealing with small things, that conversion to a list is trivial, and it makes just writing the unit test easier. But in production, it can still have all the advantages of a generator, the performance advantages and resource usage advantages, and still behave the same way that my test indicated it would behave. So I'll test with, I'll devise tests that test all the kinds of ways that I expect it to be able to fail and make sure that it never fails. However, as your functions get shorter and shorter, one notable side effect is that I might actually look at this bottom one and say, you know what? I can look at that and know it's right. I need one unit test and I'm done. Like I need to give it a single sample input and just make sure the thing I get out is a generator, and if I iterate it, I get these values. As opposed to this top one, it's harder for me to look at it and know that one test would be adequate. I have to really think about all the ways it could possibly fail. The one in the bottom has far fewer ways it could go wrong, so the number of things I have to test is greatly reduced. Did that
Okay, yeah, that makes
help?
sense. It's
Yeah.
more of like bottom up building pieces work instead of a top down looking into your whole process.
True, although this meta pattern of decomposed function, this really ends up being kind of approaching it from both ways. I'll look at this and say, oh, there's this one thing in here that I can pull out into a separate function. Okay, that's the bottom up. But there's this other thing that when I look at it, in this case, if you do the walkthrough that I talked about that I presented for the group on Saturday, if you go back and watch that, you'll see that this code up here actually starts to show this pattern where I have content and then I pass it to a function and then I call another function on that and then I call another function on that. And as soon as I see that, that triggers in my mind, oh, this is really a pipeline. So what I really need to do is build the list of functions in order that I call and just shove the data through that pipeline then. So it makes you rethink your algorithms. If you start with completed functions like this one, it makes you rethink what the algorithm does. So a top-down approach can also have value. Any other questions? I really geek out on this stuff, so if anyone wants to stick around longer, I'm happy to go as long as David doesn't get tired of holding the meeting open.
I actually have a question.
Sure.
It's a note. So I program in the style a lot, and I think it's not really correct to say there is no state, because your state is actually in the closures and you stack. So like it's not a new variable, so it's kind of exists outside. And I find a real hard time to debug things when you have like you try to do something real and you get maybe like 100 functions, right? That intertwined in this way, and there's closures and generators, so you cannot actually step through the program or look at it because the order of execution is very not obvious. Because if you return the generator and that generator calls bunch of functions, like, I mean, it's kind of cool like that you were, but sometimes the only sane way I found to debug is just print out the values like on the entrances and exits.
What I've found, and I'll use the example of a pipeline specifically back to this. What I found with, for example, a pipeline is really what I'm testing is, do each of my functions do what they're supposed to do when called on a known piece of input? Right. So that's 1 or 2 tests per function, maybe 3 or 4, whatever. Right. And then if I were to, without running it, if I just build the pipeline with a given file name and it looks at the extensions and decides what it has to do to decode the file, if I do that, does it give me the expected set of functions back? So A, are the functions correct? B is the thing that builds the pipeline giving the right order of functions. And then I would cap that with a couple integration tests where I actually handed a real file that exists as part of my test suite. It's maybe small, but it includes the kinds of things in the file that might be problematic. And so an integration test just makes sure that, yes, it really does work with this file. It really does work with this file. And so it's a sort of a combination of unit testing and integration testing. But the integration testing is predicated, is relatively simple because it's predicated on the notion that the individual functions are behaving correctly because they're being tested separately. And that assuming that there are no side effects, knowing that the functions are right and knowing that the combination of functions is the right combination is enough to know that the pipeline is executing correctly. In every domain, there will be a way to look at it that helps you find that. But some problems will be harder to test than others. The reality in practice is that you know, any mechanism is going to have examples of things that are difficult, and my goal is to point out that there are some benefits. It's not a mecha. It's not going to solve all your problems, right? Functional programming is great, but it's just another tool in the toolbox. But by looking to remove state where you can, you reduce and possibly eliminate entire classes of bugs. You still have off-by-one errors.
But you bring a new class of, you kind of trade one class of bugs for another. Because with pipelines, it's great, but if you process is very branchy, like, so it's not like a straight pipeline, but it's branches, and you have generators, like, so lots of deferred executions. It's kind of not obvious to see.
Yeah, and sometimes the right answer is, we figure out how to write the test that tests this thing, or the combination of tests. And sometimes the right answer is, if it's hard to test, maybe it's time to look at a different approach to solving the problem. And I'm not going to say that either one is true in your case, in a specific case, but like, it's an opportunity to look at it and say, are we really seeing the problem correctly? Is there a more elegant way to get to a solution? But yeah, you're right. There will be difficult examples in any paradigm that are hard to test, and functional replaces some with others. I contend that the kinds of things that functional programming introduces are less complicated to solve than the same solution in an object-oriented manner. Ultimately, what I'm looking for is a paradigm that gets me closer to the right answer faster, and I've found in general functional programming does that. But it does, you know, it will still have, yeah. So. Great. Well, thank you, everyone. I will stick around, but I do want to at least say, if anyone wants to screenshot this slide, I highly recommend all these links. I'm the one at the bottom. I put me at the bottom because I'm less important than everybody else. But the two talks I talked about, the Wikipedia article on Lambda Calculus is really helpful. Python has a functional programming how-to, which oddly I read after I wrote my talk, and I realized that half of what I was saying is almost exactly what they say in the page in the order they say it. So I promise I didn't lift it from there. But essentially they'll reiterate the same things. Here's why you might want to look at these approaches, some of the benefits you get from them, and some of the ways that the Python language helps you out. And then itertools is really handy when you start working with generators, when you start working with iterables in general. The itertools library is fantastic. So I recommend diving on some of these things and learning more, because at the end of the day, it just makes us all better devs. Even if you only adopt a piece here and there, you can still see benefits from even partial adoption.
Hey, Jeffrey?
Yeah.
Like the examples that you had, let's say with the evens, where you reduced a lot of code to one single line and returned something. That example you had where you checked the extension of the file to see if it was zip, and then you looked for UTF-8. Are you saying in every case, can you smush your code down to almost one line? Like this, this iterate file.
I'm saying in a lot of cases you can squish it down to one line. In my ideal world, every function consists of a single return statement, right? And everything goes in the return statement. It's either returning a generator, or it's returning a computed value, or it's returning whatever, or it's returning a function that does something. But each, you'll notice that most of my refactorings here, each function contains a single statement inside. In this case, this is sort of the exception. This one here, the with open, right? That has 2 lines of code, but most of them are just a return statement. And so what I'm doing inside that return statement is I'm declaring what the output should look like, rather than building something, because that declaration, again, in general becomes easier to test. So I can test individually if the pieces work independently of testing them together, and breaking everything into its own separate function. Whoops, wrong button, sorry about that. We'll be back in just a moment. There we go. Breaking big functions into lots of smaller functions just makes it easier to reason about the code and test the code. So even if you don't take a functional programming approach, just looking at how to decompose, and so there's one thing you'll talk about here, you probably heard people talk about algorithmic complexity. And for example, this has a complexity of 4, I believe. No, 2. This has a complexity of 2, which means if you wanted to test the entire code path from start to finish, you have at least, at a minimum, 2 tests you have to write. One to test if the if is true, and one to test if the if is false. And if you have lots of if statements in something, that means you have to test lots of different variations to see that your function's working right. It's easier to decompose it and have each individual function do the right thing and have some selector that decides which of those functions is the one that's chosen. That ends up being easier to test. So it's just looking for where you have big methods and breaking them down into small methods that are more understandable.
Jeff, different question.
Sure.
If you have, let's say you have a new programmer that's coming on board, and you want to say, this is the program and this is how it works. Do you have or do you maintain a model that shows how the overall program flow exists and how each of these functions fit into that program?
So yeah, there's no right answer here, right? However, I'm going to say that because a lot of my background is test-driven development, I prefer an approach where the tests are also the instructions about how to use the code. If you look at the tests, they show you how functions are intended to be called. They show you what the expected results are. But the combination of looking at a test and looking at a function should be enough to make sense of that function. And rather, like, I will also have big picture views like architectural diagrams and flow diagrams and that sort of thing. But I will try to aim for an architecture where the flow is described in events, and those events each have a very deterministic way that they're handled. And so each event essentially is a function or a collection of functions. Then when a new developer is learning about it, I can pick one event at a time. Let's talk about this transformation. Let's talk about this transformation. And over time, they build up the bigger picture of how they all go together. So I like to focus on, rather than trying to see the big picture, let's get you working on one little piece and just expand scope over time as they get more familiar with the code. But that would be true, I think, with object-oriented too. I don't think that's unique to functional.
Okay, well, that's sort of, in a way, that answers my question, because when I think of an event, you said an event has a whole bunch of different functions. Well, that's the same way when I look at your iterate file, your first example, that explains all of the different things. It may be more difficult to test, but it explains what all is happening. Mm-hmm. And so if you've got a program and you've got, let's say, 50 different types of events, then you could say, well, here's one event, and here's everything that goes on with that one event. And then you go on to the second event and say, well, if you're not doing this event, you're doing this other event here, and these are all the functions that. So basically, it's a way to look at the architecture and break the architecture down.
Sure. So
that you can understand what the whole program is doing. Whereas if you just said, all right, here's my program. I have 500 functions. Figure it out.
Mm-hmm. Well, so you also have other signals you can send people. So for example, if you have, the example I'll use actually is the one I do in the course, that I did in the course on Saturday. We're parsing a file. It's a CSV, but it might be inside a zip container, right? So we have to, and this is what this iterate file here is from. What I ended up doing, this build pipeline function, is where that logic happened. And the way that I solved it was, for each extension, I basically had a dictionary at the bottom of the file that said, for this extension, here's the functions that you use. For this extension, here's the functions that you use. And it hard-coded them out. And if you had 3 or 4 extensions in a row, like, and I showed this example specifically, .csv, .tgz.zip. So it's a CSV wrapped in a zip, and that zip then is wrapped in a tar gzipped archive.
Yeah, I saw that.
Yeah, okay, cool. So it essentially, rather than having logic to say, how do I know what, rather than having conditionals to say, is it this case or this case or this case, I crafted in a way where I have a lookup that says, oh, that case, that's hard-coded, that's this combination of things. And you can just chain them together to get the bigger effect. That's a strange way of looking at it if you're not used to the paradigm. But once you've been working with it for even a few weeks, you start seeing the world in that way, and you pick them up very quickly once you're exposed to the syntax. It's the difference that makes it hard to read. Just like when you first started with object-oriented programming, almost certainly there were a lot of things you're like, why am I doing this? What is the purpose of this? It's the same. There's a learning curve. But another choice is within a module, you will have functions that are at the very top, essentially this is the thing that this module is about, and all the other functions inside are the helpers that make it work. For example, that might be one way to organize your code. And in that case, if you think of each module as doing one thing and having 2 or 3 methods that the outside user would call, and if you're not the outside user, then you need to know all the methods. But if you're the consumer of the class of the module, you only need to know these 3 functions. That gives you that ability to differentiate between how much you need to know to use it. For example, a new hire could be vaguely familiar with this module, and this module, but intimately familiar with the one they're working on. And as long as they are vaguely familiar with the others, that's good enough. So I still think that you don't, like, the goal is not to say, here's the code, go learn it. It's more to say, let's start you with this small subset of it. And this happens to be, from my experience, the easiest subset to start with, or this is where we have a bug right now. The bug should be easy, but I'll help you, I'll mentor you through the process as you get used to it, so you can ask the questions that make sense of what's going on. It is a different way of looking at it. And some of these things look a little bit less friendly than some of the code you may have seen in the past. I've been looking at code like this for years now, 2 or 3 years. And so to me, I glance at it and I know exactly what it's doing, but that's familiarity. I acknowledge that. But that familiarity can be learned by anybody.
Hey, Jeffrey?
Sure.
On this slide, towards the bottom where you have returned functools.reduce.
Yes.
Here's a question from left field. Is functools a compiled C program?
It happens to be, yes. Everything in functools is compiled down to machine code.
Can people make their own use this and then this dot reduce?
Well, yes. So reduce, that specific method comes from a paradigm called MapReduce. Those MapReduce and filter are like the meta functions that you can do everything with. And by everything, I mean everything. Google built Google search on MapReduce, right? I mean, you can do everything with map and reduce. It's not always the most understandable way to do it, but it always, any algorithm you have almost certainly can be solved with some combination of maps and reduces.
Like if you were on the scale of a Google or an AWS or a Netflix, and you're doing something where you really need to budget your RAM, do you write your own things to pip, your own functions?
No, I usually trust the language to do it right. The things in functools and the things in itertools are going to be way better than anything I can write because they are compiled down to machine code already.
Yeah.
Like, and by people who know how those are supposed to work way better than I can, right? So they will have done a better job. If I see that I have one function that happens to be particularly slow in Python because what it's doing is just not conducive to Python, then yeah, I might write a C extension to implement that piece. But I would look for somebody else's library. Like, can I do it with NumPy or can I do it with Pandas? Because if I can do it there, they've already done that work. And again, I can just take advantage of that. So yes, you can extend the language to do anything you need. In practice, I've found the kinds of latency you get because of poor algorithmic choices when your algorithms are working on very small subsets of data rather than trying to keep the whole picture in mind. The performance implications become less in many cases, not every case. And the time you're waiting for data across the network usually ends up being far greater than the benefits you get from trying to performance enhance your code. So if you really isolate your code, and like in a cloud functions environment is the prime example of this. If each of your functions does one thing well, and by itself, it's very simple to understand what it does, and it's not depending on huge amounts of data to complete its task, then even if the overall work being done is very high, any one of those functions is still chunkable into something that the average person can understand. When I have this event happen, I do this computation, I save the information here, or I go load these 3 records and combine them in this way, or update, whatever, but it's limited in scope. If you are doing something really wild, like say, building Google search, what you're doing then is distributing. Lots of computers are involved in doing a little bit of work each. And with functional programming, distribution of massively parallel algorithms is much easier because they don't depend on any sort of state from other workers. So that mass distribution of a problem across thousands or hundreds of thousands of machines is easier to reason about if you're using pure functional programming as opposed to programming that has a lot of dependencies on data or external services.